Alright guys, today's goal, the learner will understand how to solve and model equations. So we're going to focus on solving exponential equations, solving logarithmic equations, orders of magnitude in logarithmic models, Newton's law of cooling, and logarithmic re-expression. So let's take a look at some things. So here's some properties we need to know. So one-to-one properties. For any exponential function, f of x equals b to the x. If b to the u equals b to the v, then u equals v. So if you match the bases, you can set the exponents equal to each other. For any logarithmic function, f of x equals log base b of x. If log base b of u equals log base b of v, then u equals v. So again, if you have the log of the same base, you can set the u and the v equal to each other. Okay? So let's take a look at this. Alright, so first thing we got to do is try to solve this. So first thing I would do here is divide by 40. So you would get 1/2 to the x divided by 2 equals 1/8. Well, I can say 1/8 is the same thing as 1/2 to the third, because 2 to the third is the 8th. So see, now we have our bases matching each other. So what you do is this. X divided by 2 equals 3. So x equals 6. Okay, let's take a look at another one. And this should say equals 27. So first thing I would do is divide by 125. And it can't be simplified, so you get 3/5 x to the x divided by 3 equals 27 over 125. So you can't do decimals here, guys. Okay? So this is what I look at. What do I multiply? Or 3 to what power equals 27 and 5 to what power equals 125? Hopefully it is the same, and it is. So I still have 3/5 x to the third, but this would be 3/5 to the third. So you get x divided by 3 equals 3. Why? Because their bases match each other. So you get x equals 9. Okay, let's take a look at some more. Okay, solve log of x to the third equals 3. So we don't have two logs functions. So what is the base of this log? Remember when it's not there, it's 10. So what you need to do is 10 to this power, 10 to this power. Because these cancel each other out, so you have x to the third. And 10 to the third, 1,000. Cube root it. And you get x equals 3. You cannot use the power rule on this. So let's take a look at another example. So log of x squared equals 8. So what's the base of the log? 10. So you go 10 to that power, 10 to that power. So you get x squared equals 10 to the 8th. Square root. You get x equals plus or minus 10 to the 4th, which is plus or minus 10,000. Both of those work if you check them by plugging back in, so you're good. Okay, let's look at some different examples here. Orders of magnitude. The common logarithm of a positive quantity is its order of magnitude. Orders of magnitude can be used to compare any like quantities. So a kilometer is 3 orders of magnitude longer than a meter, because you'd have to multiply by 10 3 times. Okay, a dollar is 2 orders of magnitude greater than a penny, because there's those 2 decimal places. New York City with 8 million people is 6 orders of magnitude bigger than Earmuff Junction with a population of 8. Okay? Because if you wrote 8 million, it would be 8 times 10 to the 6th, and 8 would be 8 times 10 to the 0. So it's 6 greater than. Okay? Some other properties we need to go over. Richter scale. The Richter scale magnitude R of an earthquake is R equals log of A divided by T plus B, where A is the amplitude in micrometers of vertical ground motion at the receiving station, and T is the period of the associated seismic wave in seconds. And B accounts for the weakening of seismic wave with increasing distance from the epicenter of the earthquake. So here's another equation we'll probably use in some word problems coming up. pH, often talked about in chemistry. In chemistry, the acidity of water-based solution is measured by the concentration of hydrogen ions in the solution in moles per liter. The hydrogen ion concentration is written as H+. The measure of the acidity used in pH is the positive of the common log of the hydrogen ion concentration. So it's the hydrogen plus positive. So pH equals negative log of H+. More acidic solutions have higher hydrogen ion concentrations and lower pH values. Okay? Let's look at another property. Newton's law of cooling. An object that has been heated will cool to the temperature of the medium in which it is placed. The temperature T of the object at time t can be modeled by T of t equals T sub n plus T sub o, or T sub naught, minus T sub n, times e to the negative kt, for an appropriate value of k, where T sub n is the temperature of the surrounding medium, T naught is the temperature of the object. This model assumes that the surrounding medium maintains a constant temperature. Okay? So there's another equation we're going to need to be able to use. So a hard-boiled egg at temperature 100 degrees Celsius is placed in 15 degrees Celsius water to cool. 5 minutes later, the temperature of the egg is 55 degrees Celsius. When will the egg be 25 degrees Celsius? Okay, so we know T naught is 100. The Tm, where you're placing it, is 15. And we also know that T of 5 equaled 55 degrees Celsius. So if we use that fact at first, we have 55 equals 15, the T sub m, plus the original minus the room temperature times e to the negative k times t. So now we need to solve for the k. So subtract the 15 and subtract in there, so you get 40, 85 e to the negative 5k. Divide by the 85, so you get 40 over 85 equals e to the negative 5k. Take the natural log of both sides, so you get natural log of 40 over 85 equals negative 5k, because remember, you'd have the natural log of e to the negative 5k, and the natural log of e, bring that down, natural log of e is 1. Divide that by negative 5, and you'll get k. You get k is approximately 0.151. So now that we have k, we can do this. 25 equals 15 plus 85e to the negative 0.151t. Subtract the 15, divide by 85, you would get 10 over 85 equals e to the negative 0.151t. take the natural log of both sides. So you get the natural log of 10 divided by 85 equals negative 0.151t. Then just divide by the negative 0.151. So you would get t equals approximately 14.17 seconds. Or minutes. Okay, let's take a look at some more examples. Okay, guys, remember in your calculators you can do regression models by logarithmic re-expression. Okay, so you have linear regression, y equals ax plus b. Natural logarithmic regression, y equals a plus b times the natural log of x. There's exponential regression, which is y equals ab to the x. And power regression, a times x to the b. These are all in your calculator under Stat, Calc. You see them all there. Okay? So let's look at what these represent. Okay, so natural logarithmic regression re-expressed. So see how you start with the points x comma y because this curve looks like a natural log? What you do is you take the natural log of x values and then the y value. So you'd enter this in list 1, enter y values in list 2, take the natural log of x of list 1, and then you're still using list 2. So see how the data becomes a straight line as prediction there? So natural log of x comma y will equal u comma y data with linear regression model y equals a times u plus b. So it's a linear model for that. So what's our conclusion? Y equals a natural log of x plus b is the logarithmic regression model for the xy data. Okay? So exponential regression. See how when we're looking at this looks like an exponential function? That lets you know you take the original xy data and you keep x the same, but you take the natural log of y. And see how it puts it out to a line? So now let's look at what our conclusion can be. It says y equals c times 2 to the x, where c equals e to the b, and d equals e to the a is the exponential regression model for the xy data. Okay? The power regression re-expressed. Well, so far we've taken the natural log of x and the natural log of y separately. Now it's when they're together. So power regression. So if this looks a little bit like exponential, but it happens to be a power function. So you try the exponential and it wouldn't line up like this. So that's when you do natural log of x, natural log of y. And that's when you know you can use that for the model to predict. So we'll do some work with these together in class, and I'll see you guys tomorrow.